All right. Hello, my name is Mickey, and today I'm going to be starting a series of videos about mechanics on Lie groups. And to start off, I'm going to be talking about the motion of a free rigid body, which is sort of the simplest example of a mechanical system whose configuration space is a Lie group. Um, so as a reminder, um, thing we're studying is basically just some object that we'll just pretend like it's tumbling freely, zero gravity or something. All right. And this was supposed to be a rectangular prism, but it ended up as a kind of trapezium shape, but that's okay. Um, so basically, uh, at time zero, we take it to just be, in some configuration. And then at time t, we take its configuration to be the rotation matrix in SO3 that you would need to apply to space to get the body from its initial configuration to where it is at time t. So R of 0 then has to just be the identity, and then R of t is in SO3. Also, at every given time, the attitude in space is changing. So we have R dot of t, and this is in the SO3. All right. But the way that people usually talk about um, the free rigid body is by using something called body coordinates. And the idea is that the problem is simpler if instead of considering rotation matrices, with respect to these fixed axes in space, you instead consider a system of axes that move with the body throughout the duration of motion. These are the principal axes of inertia. And to give you a picture sort of what's happening, if we imagine this sort of curved surface here, I'm going to pretend that this is SO3. And then let's say this is the reference configuration. So the attitude at time zero. And then here we are at time t. And then let's say this here is our tangent vector. All right. Um, so obviously, um, it's not literally tangent to the curve right there, unless the curve is not very smooth at all. But I'm just drawing it like this so it's easier to see. And then when we work in body coordinates, we basically, uh, because we're imagining the axes are fixed, we're sort of just translating this back to the origin. We're just working in the tangent space at the origin, not with a moving like series of tangent spaces. So the body angular velocity is this, it's omega, and it's given by R inverse t, R dot by t. All right. So, but if we want to derive the Euler equations by calculus of variations, which is going to be the goal of this video, we won't just be able to, sort of blindly vary the Lagrangian with respect to omega, because we actually have to make sure that our variations of omega make sense, right? Because um, the variations usually are in like a tangent space, but we're now working with this sort of series of tangent spaces that are being translated back to the origin. So something's going to go different. So just as a reminder, the Lagrangian for the free rigid body is omega transpose. Um, actually, let me write it like this. And so if we're in the frame of if we're in the frame given by the principal axes of inertia, I1, I2, I3 are the moments of inertia, and these are the angular velocities around each of the axes. Okay, so but when we do the variations with respect to omega, let's just find the actual specific form of that. So this is delta R inverse R dot equals negative R negative 1 delta R R inverse R dot plus um, R inverse delta R dot. I didn't draw an inverse there. Right, there we go. Um, Now, this right here, this term might be slightly confusing. Like, why does the derivative look like this? But just to see why it looks like that, um, just differentiate this identity here for matrix multiplication or group multiplication, and then you'll see that uh, this is the uh, chain rule for inverses when you have something that isn't a scalar. Okay, so this right here is just omega, and then this right here is another element of the tangent space at the identity, or the Lie algebra, as it's called, and we're gonna just denote this as sigma. Okay, and this over here looks almost like sigma dot. So if we want to get everything in terms of just elements of the Lie algebra, we might try and take a look at what sigma dot is and see if we can get some cancellation. Okay, so sigma dot equals d dt r inverse delta r equals negative r inverse r dot inverse delta r plus r delta r dot. Okay, this is just negative omega sigma plus r negative 1 delta r dot. Okay, so yeah, if we just subtract this second line from the first line, we get that delta omega equals sigma dot plus omega sigma minus sigma omega, which is just sigma dot plus the commutator bracket of omega and sigma. All right, but usually omega, the body angular velocity, is thought of as a vector, not as a matrix. So the reason we can do this is because if you have a vector xyz in R3, you can map it to a skew matrix 0, c y negative x, c negative y x, like this. So we'll call this r and this little r hat. That's why there's a hat here. And you can verify it's a not too long of a calculation. Very straightforward. It's just that r, let's say we've got another element of R3V, and then we take the hat of this is just equal to r hat v hat commutator. Okay, so if we use this and we now want to talk about omega as being a vector in R3 and sigma as well, then we have delta omega equals sigma dot plus omega times sigma. Okay, awesome. our action is going to be this. And we're going to vary the action, say that is 0. So this becomes L d omega, or gradient with respect to omega, times the variation of omega dt equals 0 equals integral dl d omega times sigma dot plus dl d omega times omega cross sigma. Okay. Then with the first term, we'll do the usual integration by parts, and we're going to assume that our variations of, or that we're going to assume that sigma of 0 and sigma of t, just like in the usual case, we're going to assume that this is 0. So that when we integrate by parts, we have 0t negative dl d omega dot sigma. Okay. Or to actually integrate by parts, there we go. And then this term, so this is a vector triple product, and there's an identity that u dot v times w equals w times u cross v. Basically, you can just scoot everything over to the side by one, and you'll get the same thing. So again, the goal here, the reason I'm doing this is we want to get something dot sigma, and then we don't want to have these like mixed sigma dot and cross sigma terms. That way we can use the lemma from the calculus of variations. So this term here is going to look like plus dl d omega times omega sigma dt. Okay, and this is 0. And because it's 0 for any sigma, this means that d dt dl d sigma equals dl d sigma, or sorry, omega. I said omega there. It's meant to say omega there. Okay. D dt dl d omega equals dl d omega cross omega. Okay. And then, right, L is just this. I already write that up there. I did. Yeah. Okay. But just write it here anyway. And so now we have d dt I omega, where I is just the diagonalized moment of inertia tensor. So this equals this. Okay, and then here we are, we're done. So these are the Euler equations for rigid body motion, and got them from a sort of variational principle for Lie algebras. Right? So what we did was we just made sure we had to take the right kind of variation. And then once you've solved this for omega t, you can then go back to this equation here. We know omega t, so we just solve a, well, not just solve, we solve a matrix ODE. And that actually, it looks simple, but this ODE is actually still hard to solve. But I might talk about that in a later video. Yeah, the bulk of the dynamics has been solved, or can be solved here. I haven't solved it, but okay. So this is like pretty nice. And it turns out that you can do this with a lot of different systems on Lie groups. For example, the motion of a perfect inviscid fluid is basically just go through the same procedure, more or less, except instead of working on the Lie algebra little SO3, you work on a Lie algebra that I sometimes see written as S vect, which is the Lie algebra of S diff. So these are sort of an analogy with SO3. It's special diffeomorphisms, I guess, or diffeomorphisms that preserve volume. And the Lie algebra is vector fields with zero divergence. But yeah, if you do this whole procedure on this, which I'll show in a couple of videos, you get the Euler equations for the motion of a perfect fluid. Other examples are the KdV equations, which are or the KdV equation, which is a PDE that describes shallow waves and in one dimension. The rigid or the Lagrange top, which is a rigid body that is now acted upon by gravity. And there's many other examples, but in the next video, I'm going to talk about the Hamiltonian side of this picture here. So I hope you enjoyed, and I will see you next time. Thank you for watching.